So we start talking about organic compounds today. And to make your life sort of easier, our focus will not be on as much the reactions of organic compounds. There will be some, but more on the types, the classifications, the functional groups, and so on and so forth. And obviously, first we need to define what does it mean for a chemical compound to be organic. Okay? So the very first group of organic compounds that we're going to chat is hydrocarbons. So the key thing, I'm going to skip all that stuff. The key thing about organic compounds is that they contain always two types of atoms, at least two types of atoms, carbon and hydrogen. Okay? Can there be other atoms? Absolutely. Anything from various nonmetals like halogens or sulfur, nitrogen, boron, phosphorus, but also even metals, so-called metallo-organic compounds. By and large, the number of organic compounds that surround us, you can see what I'm highlighting, way more than the number of inorganic compounds that we have to deal with in our day-to-day basis. When you look around yourself right now, the paper that you're writing on is organic. It's made out of cellulose. Your laptops, at least the keyboard and you know the body of the laptop, they're made out of plastic, which is organic. The boards on the tables that you are sitting at are organic. The chairs, at least the the seat itself and the back support are organic. Your clothing is organic. I could go on and on and on. Okay? When we write a formula for any organic compound, we always start with a carbon, then hydrogen, and then everything else, usually oxygen, and then whatever we have left. Okay? Now, organic compounds share a lot of common features. The bonds within organic compounds are covalent, bonds between carbon and hydrogen, carbon and oxygen, oxygen and hydrogens, and other atoms. Usually they have relatively low melting and relatively low boiling points. Now, the reason why I use term relatively, of course, it depends on the compound. If you talk about hydrocarbons, low molecular hydrocarbons such as methane or ethane, those are gases, obviously, low melting point. But even organic polymers, like the boards of this table, have a relatively low melting point. Most organic compounds can be burned. They can undergo the process of combustion. Again, how readily? A different question. Gases like methane, ethane, or propane will burn readily, while to burn any polymer, it's going to take a little bit more effort than that. And most organic compounds, I wouldn't say all of them, but most organic compounds are not water soluble. So we can consider them being non-polar, I'm sorry. Okay? Now, I'm not sure I fully appreciate the correctness of that comparison between the salt and propane, because it doesn't really make sense. What I would suggest, the comparison between, seriously, instead. Do you use salt in your kitchen? Do you use sugar in your kitchen? Do they look alike? Did you ever mix them up? Probably so. Well, I did. But if you will take a pinch of salt, put it in a teaspoon, and heat it over the gas stove, Well, nothing's going to happen. If you take a pinch of sugar, put it in a teaspoon and melt it over the gas stove, it's going to melt. And you can even burn it. Like it's going to, like in some alcoholic cocktails, they fire up the sugar. Same idea. So they may look similar, they may have the similar function, but inorganic and organic compounds are drastically different. Okay? So I would highlight some of the differences. Yes, well, inorganic compounds, not necessarily ionic. We can think of, I don't know, boron nitride, for instance, okay, or hydrogen chloride. They're not necessarily ionic. So this is what I would highlight. First of all, the difference in elements. Okay? All organic compounds are molecular, while inorganic can be ionic or molecular. Bonding, yes, organic compounds are almost entirely covalent, while inorganic compounds can be ionic, can be covalent. Bonds, well, in organic compounds, they are nonpolar unless a strong electronegative element is present. But if you think about a majority of organic compounds that can be found around you and in living organisms, practically all of them contain oxygen or nitrogen atoms which are strongly electronegative, which means there is a fair amount of polar bonds in organic compounds. In inorganic, you're going to have ionic, you're going to have a bunch of polar covalent, and very few nonpolar covalent. Now, the next idea is true. Melting points for organics, usually low. For inorganics, usually high. Again, depending on what you're focusing at. And inorganic compounds mostly are not water soluble. Well, maybe 50-50, maybe, a little less of organics are water soluble. Now, inorganics are mostly soluble in water. Okay? So the simplest class of organic compounds are hydrocarbons. These molecules consist only of carbon and hydrogen atoms. Okay? Sounds good? And one of the fundamental differences between organic and inorganic compounds is the number of bonds that carbon can produce. When we talked about inorganic, I mentioned that, for instance, there's a carbon monoxide, a molecule in which carbon forms 2 bonds. Of course, there's carbon dioxide in which carbon forms 4, but to be fair, the orientation of the bonds in the simplest hydrocarbons is very specifically defined. So these bonds are oriented as a tetrahedron. Do you know what tetrahedron is? The answer no is perfectly acceptable. No? Okay. Do you know what a pyramid is? Like a pyramid, right? You understand what the base of the pyramid is? Like Egyptian pyramids, the square at the base? Now imagine, replace that square with a triangle. Isosceles, like all sides are equal, triangle, but have a pyramid. This is a tetrahedron. So at the center is carbon And at the angles, at the, the pointy things are hydrogens. Does that make sense to you? So hydrocarbons can be saturated or can be unsaturated. And we use the term saturated when there are only single bonds in the entire molecule. If you have questions, interrupt me, please. So the simplest hydrocarbon is methane. It consists of one central carbon and 4 hydrogens positioned in the corners of that tetrahedron.
So tetrahedron basically just means like 4 triangles?
Yes. 4 isosceles triangles, triangles with equal sides, that are assembled in a 3-dimensional structure. Good?
Yep.
Okay. So, you can represent a molecule of this organic compound, methane, in many different ways. So on the leftmost one is so-called space-filling model. Now we are going to play with ball and stick modeling in the lab, and I personally like ball and stick better than anything else. Okay? Now, wedge dash model. So let's talk about wedge dash. I'm going to explain how it works, all right? So the screen that you're looking at represents a vertical surface, a plane. Everybody agrees? If a bond lies within that